Today we're going to be doing something a little bit different, and it's something that brings together many ideas in computer science, and it's the idea of program correctness. So what we're going to be thinking about is what does it actually mean for a program to be correct, and then how can we specify and verify that in some kind of precise way. So that's what we're going to be thinking about today, program correctness. We're going to come at this problem by means of an example, and the example that we're going to look at is a simple compiler. So what a compiler does in computing is it's a program that takes a high-level language and translates it down to a low-level language, which is more easy for a machine like this one to execute. So what I'm going to show you is a little Haskell file which I've written, but it doesn't matter if you don't know anything about Haskell because it's really incidental to everything that we're going to talk about today. It just allows me to do everything in quite a concise way, but actually you can do everything in any old programming language that you like. But I'm going to explain everything as we go along anyway. We have two data type declarations, and we have three function declarations, or function definitions rather. And what we're going to do is we're going to explain what these do by means of some simple examples. And then we're going to think, well, what does it actually mean for the compiler, which is embedded in this code, to actually be correct? So what we're going to start off looking at is the source language for the compiler. And it's going to be a very simple language. It's going to be the language of integer values combined using an addition operator. So we're going to be building up simple arithmetic expressions, things like 2 plus 3 plus 4. So here is the data type declaration for this in Haskell, and it's got a few components, so we'll work through these. So we're declaring a new data type called expr for these simple arithmetic expressions, and then the data type has two constructors for building expressions. It's got a value constructor, which takes an integer parameter, and it's got an add constructor, which takes two sub-expressions as arguments. So this is how we're going to build up our simple expressions, and they're really expression trees. And you might be thinking, well, what does deriving show mean here? Well, this is a little bit of Haskell magic, and it just instructs the system to be able to print these things on the screen so we can view them. So not everyone's familiar with Haskell, so I'm going to give you three little examples of values in this expression data type, and these are going to be running examples that we're going to be using throughout the video today. So the first one is going to be E1, and it's just going to be a simple integer value. So we have an integer here, 1, and then we tag it with the val constructor, and then we've called it E1. So we don't need to type this in again. Whenever we type E1 now, it just stands for val of 1. Our second example is going to be an addition. So we're going to do add of val2 and val3. So this is like how we would represent 2 plus 3 as a value in our simple expression data type. So we've got a number of components here. We've got the value 2, and we've got the value 3, and then we combine them with the add constructor. So it's a little bit more verbose than what you'd normally write down in mathematics. You'd normally just write down 2 plus 3, but here we're doing it in a programming language, so we need to be a little bit more verbose, and we're using the two constructors of the expression data type. So just as one final example, let's do something a bit more sophisticated. Let's reuse E2 and add that onto val4. So we defined E3 here to be the sum of E2 and the value 4. So what this really is it's 2 plus 3 plus 4. And we can use the little pretty printer here, which we got from writing deriving show. And if we print out the value of E3, what you get is you get the addition of 2 and 3 here as the first parameter to the add. And then as the second parameter, you have val4. So these are three little running examples of arithmetic expressions which we're going to put into our compiler as source expressions. So the next thing we're going to think about is what do expressions in this language actually mean? And this is very simple in this case. Expressions just denote simple integer values. So we can think about evaluating an expression. So let's look at the three examples. So we had E1, and if we evaluated E1, we just get rid of the val constructor and we get the value 1. Very simple. If we look at our second example, which was 2 plus 3, if we evaluate 2 plus 3, then of course we're just going to get 5. And if we look at our third example, this is 2 plus 3 plus 4, a bit more verbose, but when we evaluate this one, we're going to get the value 9 as we expect. So let's have a look at the source file now and think, how do we actually define this evaluation function? And it's actually just a very simple two-line recursive definition. So let's look at the two lines one by one. So the first line says, if we evaluate a value n, we simply remove the val constructor and we get the underlying value n. The second line says, if we evaluate an addition of two expressions x and y, all we're going to do is evaluate the first expression, x, evaluate the second expression, y. That will give us two integers, and then we can add them together, and that will be the evaluation of the integer. So it's a very simple two-line recursive definition. The next thing we're going to look at now is the actual compiler for these simple arithmetic expressions. And what it's going to do is compile from expressions down to code. And the code is going to be a sequence of operations for a very simple stack machine. And a stack is just like having a stack of books. It grows and shrinks, and you always put new values on top of the stack. So let's have some examples to see how the compiler works first, and then we'll see how it's actually defined in the code. If we think about our first example, value 1, we can compile that one. And what we're going to get is just a sequence of a single operation for the little machine. And what the operation is going to do is just push that value 1 onto the stack. If we look at our second example, we had add of 2 and 3. If we compile that, then we really start to see what the compiler is doing. It's compiled it down to a lower level sequence of operations. And in this case, what we're going to do is we're going to do a single push of the value 2, another push of the value 3, so that will have two values sitting on the stack, and then you'll perform an addition on those two values, and that will leave the value 5 sitting on top of the stack. So you start to see how the compiler here is taking high-level arithmetic expressions and compiling them down to lower-level sequences of operations, which a machine like this one could more easily execute. So let's have one more example. Let's look at our third example, 2 plus 3 plus 4. If we compile this one, then we get 5 operations this time. We have push of 2, push of 3, and then add, and that will leave the value 5 sitting on the stack. And then we push the value 4, and then we perform an addition, and that will leave the value 9 sitting on the stack at the end. So that's what the compiler does. Let's have a look to see how it's actually defined. And again, it's just defined as a simple two-line recursive definition. So if we look at the base case for the recursion, what it's saying is if you compile a value, this is very simple. You just simply emit a single instruction or a single operation which pushes the value n onto the stack. Whereas if you compile an addition, then you have 3 things to do. What you're going to do is you're going to compile the first part of the addition, compile the second part of the addition, and then put an add operation on at the end. And the plus plus here is just a way in Haskell of combining lists together. It's list concatenation or list append. And this then brings us to our second data type declaration at the top. We're defining the data type for operations, and this is very simple. There's no recursion involved this time around. It's just simply you push an integer value onto the stack, or you can perform an add on the top 2 values on the stack. And again, we're using the Haskell magic here to derive a pretty printer which can print these things on the screen. So that's the compiler for arithmetic expressions. But we're not quite done yet. We still need to think about how does code for this little stack machine actually get executed. So again, let me give you some examples of this, and then we'll see how this is actually implemented in terms of Haskell code. So if we take some examples here, so the first example is just going to be if we execute the result of pushing 1 onto the stack, and we give it the empty stack, then you just get exactly what you expect. You get the value 1 sitting on the stack. And remember, a stack is like a pile of books. In this case, it's a pile of integer values, and you always put things on the top. Okay, so in this case, we're just taking an empty pile and then putting the value 1 on the top. Let's take another example. Suppose we did push 2, push 3, and then add, and we executed that with an empty stack. Then we get the final stack with the value 5 on it. So the way this will actually get executed is the value 2 will go on the stack, then the value 3, then you'll add them together and you'll get the value 5 sitting on top of the stack. And that's exactly what we get sitting here. So the very last example, if we did the 2 plus 3 plus 4 example, so I do push 2, push 3, perform an addition, push 4, perform another addition, and then hopefully we get the right result, which we do, which is the value 9 sitting on the stack. So this kind of shows you how the little stack machine actually works. So let's have a look at the code for this. So the code looks a bit more complicated, but it's actually completely straightforward, and we can just kind of talk through this. So the way, if we want to execute a push, and then we have some more code afterwards, in the context of a given stack, is we're simply going to put that number on top of the stack, and then continue executing the remaining code. So very simple. If you want to execute a push, you put that number on top of the stack, and then you just continue with whatever it was you were going to continue with. The second case says, if we're trying to execute an addition, all we're going to do is inspect the top of the stack and hope that we have at least two values, m and n, on top of the stack, and s is everything else. And all we're going to do is add together those two values and then put them on top of the stack, and then we'll continue by executing everything else that we're going to execute. So again, very simple. If you perform an addition, you take the top two values off the stack, add them together, and put the result back on. That's all that's going on here. And the very last case is kind of the catch-all case. It says if you've got any other code sequence and any old stack, then there's nothing to do, you just return the stack. So this brings us now to the issue of compiler correctness. So what we've defined now is we've defined a syntax for our source language, which is simple arithmetic expressions. We've defined our target language, which is stack machine code for a simple stack-based machine. And then we had a compiler which translates arithmetic expressions down to the simple stack machine code. But how do we know the compiler actually does the right thing? That's the point of this video today. We're thinking about program correctness. How do we know that our program for compilation actually does the right thing? So that's what we're going to think about now. So let's look at our most complicated example, which was 2 plus 3 plus 4. So there's a bunch of things we could do with this. We could evaluate it, and we get the result 9. Very simple. We could also compile it, so we could translate it down to some stack machine code, and then we get push 2, push 3, add, push 4, and add. And then we could execute that stack machine code now. So what we could do is we could execute the result of compiling that expression using an empty stack, and what we get is the value 9 sitting on the stack, which is exactly what we expect. And you can see here by looking at these examples, the essence of what it means for this compiler to be correct is that when we compile an expression and then execute the resulting code, we get basically the same value as when we evaluate it. So in each case, we get the value 9. In the evaluation case, we just get the integer just sitting there on its own, whereas in the compilation case, we get a stack with the value 9 sitting on it. So this is the essence of what it means for the compiler to be correct. If we compile and then execute the code, it's the same as just evaluating the original expression. So what we can do now is actually think about making this precise and kind of precisely specifying what it means for the compiler to be correct. And then we can wrap things up by thinking, how could we actually verify that? So what I'm going to do is write down a simple function definition which captures what I've just said about the compiler being correct. So I'm defining a little function called correct, and it's going to take an arithmetic expression e as input. And what we're going to do is we're going to execute the result of compiling that expression with an empty stack, and what we want is that that's the same as the stack we get by just putting the value of that expression into a stack on its own. So this generalizes what we just had. What this is saying is if you compile an expression e and then you execute the resulting code using an initial stack which is empty, then what you expect to get is just the value of the expression sitting as a single little value on the stack. The double equal symbols here is just Haskell's operator for checking whether two lists are actually equal. So this captures in a very precise, concise, mathematical way what it means for this compiler to be correct. But how can we actually check that this property is actually true? Well, if you were eagle-eyed, you might have noticed right at the top of my file, I was importing the Quick Check library. And Quick Check is a random testing tool, which Computerphile's already done a very nice video on with John Hughes, which you might want to check out. And what Quick Check does is it blasts random test cases through properties, and it tries to check that the property is true for all of these test cases. So we have a property here. We've got a simple compiler correctness property. So what I can do then, I can just write Quick Check the correctness property, and it will run 100 test cases through it. It will start with very small things like just simple values like 0 and 1 and 2 and so on, and then it will consider larger and larger expressions with more and more additions. And it's trying to find an example which breaks this compiler correctness property, but it doesn't do it because the compiler is correct. Maybe it was a fluke, maybe we can try it again. Let's try 2 or 3 different runs. And in fact, it doesn't matter how many runs we do of this, this is always going to work. Okay, because the compiler is actually correct. So suppose we'd messed up. Suppose we had a compiler which we'd implemented incorrectly. So let me break the compiler now. Let me change the compiler, and this is a very easy mistake to make. Rather than compiling an addition by compiling the first thing and then the second thing and then omitting an add operation, what I'm going to do is put the add operation in the middle. And this is a kind of very common mistake. If you teach compilers to students, this is a very common mistake that you see in their code. but it will break the compiler correctness property. So this compiler is now incorrect. Let me quick check it. And it's managed to find the counterexample. And in fact, any addition will break this compiler if you work through the details. What we've seen here now is how, in a very simple way, you can capture the correctness property of a small but interesting program, a simple compiler, and then how you can actually verify this or give high confidence that this is actually doing the right thing using an automatic testing tool such as the quick check system. If you wanted to do this properly, of course, you could do some kind of mathematical proof that it's also correct, or that it's correct, using some kind of induction. Or if you wanted some machine assistance, you could use maybe an automated theorem prover or an automated proof assistant. But actually, for many applications, just doing this kind of high confidence activity of using a random testing tool like QuickCheck actually gives you very strong confidence that your programs are actually correct. But ultimately, the gold standard is always to do a proper inductive proof, or to use some kind of proof assistant to do it for you. Okay, so just to summarize what we've done today, we've been looking at the problem of program correctness. And what we've shown is how you can prove a simple compiler correct. And the way we came at this is we first of all defined what the source language for the compiler was, which was simple arithmetic expressions. Then we defined what the target language was for the compiler, which is simple stack machine code. We defined a semantics for both of those languages. We worked out a way of evaluating expressions and executing code, and then we had a compiler which translated from one into the other. And then finally, we formulated this simple correctness property and used the quick check system to check that it was correct with high confidence. And of course, if you want to do this properly, you could do a mathematical proof using some form of induction, or you could even use some kind of mechanized proof assistant. And maybe those would be interesting topics for other computer files another day. So that's it for today. See you again next time.
Blue got a cost of 3. Blue links to black, got a cost of 1. There's our routing network that we're going to work with. Pretty simple, but the routers need to find their way through it.
It still doesn't work. So now we find another example where packing and unpacking failed. And this is actually